Good morning.
One, two.
Thank you. When I was invited to this forum to make a presentation, I was thinking of what to say about additive manufacturing that could be a bit different from other presentations. And I wanted to focus, to make a focus on the point of view of the potential supplier. So this is the motto of this presentation. In this kind of presentation, I tend to make a first slide with the definition. This is a definition I found that for me it's quite good, because we have the additive manufacturing that has to cover 3 points. First is that the part to be fabricated is sent directly to the machine from the computer, from the systems. The second is that there's no need for any tool for the fabrication apart from the machine itself and all the equipment. And finally, that the fabrication consists of the addition of layers, one on the other, and the consolidation of them. And also, I would like just to bring here a set of the most common technology that fits with this definition. We have selective laser melting and electron beam melting. These two technologies are quite similar because of powder bed and metallic for metallics. The difference is the energy source, electron beam or laser beam. Also, selective laser sintering, that is for polyamides mostly. High deposition rates technologies, in which we can find wire plus arc, additive manufacturing, and direct melting deposition. And finally, fuse deposition modeling. We can divide them in metals, plastics, powder bed, and wire or powder feed technologies. These different material conditions and energy sources leads to different characteristics in material properties or achievable tolerances. And these differences would impact in the use we make for this manufactured part. So the better technologies in the geometry point of view, as SLM and SLS, could be fine for flying parts. Also, FDM is good for flying parts, but also for tooling. But the high deposition rate technologies are most useful for pre-shapes and for repairs. So these technologies with these characteristics lead us to characteristics of the part manufacturer. So we can find that the lead time of the part can be reduced just because industrialization is not so important, because the model goes directly to the machine to be fabricated. Also, there is a freedom in the design that make possible the use of topological optimization techniques for weight savings. And finally, there is no recurrent cost because the tooling is not needed, and also in recurrent costs for the material that we are saving. This characteristic of the part will imply also that there is some application that will be common to any industry. For instance, prototypes. Prototypes, since there's no tool to be fabricated, we have a reduction of lead time and also in the cost. This makes the possibility to test different prototypes for a final design. Also for tooling, because if one need is found in the shop, it's possible to design a couple of tools and be fabricated in-house machines. Finally, for low stress and highly complex parts, it's possible to avoid the utilization of any tool. It's possible to refine the design, and also to make them lighter if we make some internal structure to make them stiff enough with the less material as possible. Here we can find a couple of examples. The first are vortex generators that would replace some fins in the rear part of an aircraft. These were made by polyamide, and it took about 2 days just to be fabricated with no tool at all. The second is a drilling template that was fabricated in-house It is the third version of this template, and it could be also, it's plastic, so it's cheap, and it's quite light. And finally, we have an air duct that now is fabricated by 4 parts, 2 metal parts and 2 glass fiber parts that has been joined together with all the operations that this means. So we are considering changing to polyamide because it will be cheaper also and faster to fabricate. Okay, up to now we have seen what is common to any industry, but I wanted just to focus a bit on aeronautics. This is for the structure and the basic equipment of an aircraft, which is the sharing of the different technologies. So the bigger part is for machining and turning, and pipes and welding has also, it's quite important. But I want to point that this has to do with the amount of part numbers, not about the weight, because sheet metal forming has to do with the skins. The skins are quite big, so in amount there are not so many part numbers, but in weight they are. So this table is just a rough classification. If you consider special cases will differ a lot from this, but more or less you can see how the different technologies appear. The traditional technologies share the manufacturing space in like an ecosystem, so they don't compete one with others. So you can compare any line with the additive manufacturing line. So the first conclusion is that the non-recurrent cost and the lead times could be the key for the implementation of these technologies, and that inspections and the post-treatments, speaking in aeronautics, could be also a handicap for the deployment of the technologies. So we have seen this this sharing of technologies. This sharing of technology has to do with the materials and the type of parts we use. But these parts, all of them, share a common point, that is that they should be as lighter as possible, because as lighter is the part of the aircraft, the lower the weight of the aircraft is, the larger would be the range of more payload we can carry. This is an example. This is a pulley support. It's fabricated originally by casting, by aluminum, and we could save more than 35% in weight. I have to say that unlike other subtractive technologies for which the material has to be subtracted from a plate or a raw material, for additive manufacturing, the lighter or the lighter the part is, the less time it requires to be fabricated. So in this case, the weight saving is favored by the technology from the economical point of view. This is another example. This is an actuator fitting that has been designed. Here the weight saving is not so impressive. It's above 20%, but here we find there is a lot of reduction in the fasteners. The installation of a fastener requires precise drilling with the possibility of mistakes and so on. So in this case, it's not so important the weight saving, but the reduction of the fasteners. Well, there are another savings that have not to do with the weight. For instance, if we consider that the welding process for the materials in aeronautics is not so common because, for instance, titanium has problem with, it's very sensitive to atmosphere, and aluminum, so weldable aluminum, presents a low strength. Normally, the construction of structures has to do with the fastening, drilling, fastening, and so on. So with a middle-sized part fabricated by angles and so on, a possible saving is just to integrate in one unique part. Another saving has to do with the materials, because some materials are so hard that the machining, for instance, is quite energy and time demanding. Next, we have aeronautical companies are forced to obligate to maintain the spare parts in the entire life cycles of an aircraft. So this means that if a part needs of a tooling to be fabricated, this tool should be all the time in maintainability. It should be, from the quality point of view, to be checked from time to time. So it takes time, of course, it costs. Finally, if you consider some kind of very special materials that the major part of the material is wasted in chips, for instance, for machining, you need 8 kilos, about 8 kilos of a plate to take 1 kilo of part. For additive manufacturing, it is 1 kilo of part requires only 1.5 kilos to be fabricated. And I would like also to talk a bit about the constraints that additive manufacturing has in aeronautics. Because unlike other industries, the fatigue is a concern that's applied to every point in the structure, not only related with wheels, for instance, in automotive or whatever. Now the pressure to lower the weight force to the parts to be quite stresses. So now the fatigue is not local, but it's general. Also, fatigue is quite sensitive for internal damages. And traditional surface inspections, like adherence or dipenetrant, are no longer valid for additive manufacturing. This is because it's not possible to find out any defect. And I'm not talking about only porosity. They have been documented many other discrepancies in the internal volume of the part. And also, the roughness is a point to be taken into account, because the cracks can be originated in the surface of the part, and it has to be polished. But the point is that if the topological optimization is fully used in the design, it's not possible to find to access to all the parts of the part, to all the surface of the part. And finally, we have to consider that this surface polishment and also the heat, that's a hot isostatic pressure, is a procedure to close the voids or to repair any internal defects. There are not so many suppliers, so when there's only few suppliers, the cost of a service is increased, and this impacts directly in the cost of the finished part. 2 more points, just to keep in mind that in aeronautics, all the materials and all the material suppliers has to be qualified. This qualification process is monitored by EASA in Europe. So if you consider that we have a raw material that can be powder or wire, but we have a built-up material that is the material that takes part of the part, then the part manufacturer in reality is becoming a material manufacturing. So the qualification goes through a material qualification instead of a part qualification. And finally, if we consider traditional manufacturing technology, the ratio between inspection and post-treatment and the cost of the part is about 60–65% for manufacturing. But in case of additive manufacturing, the weight is on inspection and post-treatment. So this could discourage any potential supply, because it could find unfair that has to supply some procedure that has the bigger amount of the cost of the part and for sure of benefits. Well, I take Galileo's famous phrase, and yet it moves, because the spirit of this scary story I'm telling, there are many stories of success. The first has to do with polyamide air ducts that are being included in Airbus helicopter. There are many parts that have been designed for polyamide, not only as a prototype, but in the series production. Next one is a repair of the engine blades. for aircraft. This is a procedure that is already certified. Just as curious, I have a video that you can put. It's from the University of País Vasco. It's a test they made about the temperature. It's possible to put the video. It is a high deposition rate. In this case, is DMD, direct metal deposition. No. So it's a real example of the way to repair an engine blade. First, there is deposited some layers of material, and afterwards, a machining process is required to leave the blade to the final geometry. Okay. And the third example that I bring here is a double wall elbow for the fuel system. This has been done by our colleagues from Bremen. This video is quite impressive. In this case, it's selected laser melting, the technology used here. Our colleague could demonstrate that it's possible, a substitution of a very complex part that needs a lot of hours to be machined and to be substituted by a titanium additive manufactured part. Well, and now I would like just to talk a bit about the current development, because additive manufacturing is growing, and not only because some patents have expired that can reduce the cost of machines, but also because the people is finding the niche, the proper niche for these technologies. But the point is that these technologies shall be not only be mastered in the sense that we are able to get some material characteristics in terms of roughness or strength, but it should be also necessary to understanding how the physics goes with these technologies. So the first development is to master the process. The master process has to be outlined, because there are some differences between different industrialization concerning where to locate inspection, which kind of inspection. Is it necessary stress relief treatment if the hot static pressure is applied and so on? The second point of development is the surface enhancing, because we know that there are some non-proprietary processes that can get mirror finish for the part, but this is like a black box, so it's not possible to demonstrate in front of the authorities that this procedure can be certified. So this development of the surface enhancing is ongoing still. I have talked about inner volume inspection. Microcomputer tomography seems to be the most promising technology, but perhaps for some cases it could be possible also to substitute by a simple X-ray image that to be post-processed. But the point is to define in which cases it's just possible to make an X-ray, because microcomputer tomographies cost a lot of money for every single part to fabricate it. Then the qualification of new material is continuous, because new requirements, new needs appears to have new material that can satisfy these needs. So the qualification is all the time ongoing. And finally, the improvement on the cost, because I'm not talking only about recurrent costs, but also the cost related with the facility refurbishing for powder or for some product that can be explosive, like the aluminum powder. And just for conclusion, I want to say that there are many fancy parts that can be seen perhaps in the stores there, or incluso a motorbike I saw last week, made by our colleagues from AppWorks. But in reality, for flying parts, the qualification process should be a more conservative, a step-by-step process in which we will go from ISO design to a fully optimized design. We will go from a low critical part to intermediate fatigue-loaded part, and so on. Also, about the new niche for these technologies could be in case of very highly customized products where the agility is the key. Perhaps that could be, if we relax the inspection and the post-treatment requirements, perhaps the lead time could be enough to compensate the cost of fabricating. And for sure, it's necessary to reduce the cost, because the offer is not so big that when the offer is low, the price are higher. And this is also for the number of suppliers. If the number of suppliers are higher, then they can find better offers for machines, for powder provider, and so on. And the change of paradigm, in the sense of that the part manufacturer becomes a material manufacturer, and the point that the radius of the weight of inspection post-treatment is so high in this technology should imply that the suppliers, the part manufacturer, should be more involved in this inspection and post-treatment processes, because I'm not saying that should be internalized, but at least they should acquire the sufficient know-how to can discuss with the supplier the cost of them. And finally, it's very important to have an accurate quotation of the part. On one hand, not to discourage the employee of this technology if the quotation is too high, too conservative, but only for not to frustrating the people with not so too optimistic quotation that has not paid attention to all the factors. And that's all from my side. Thank you for your interest.